So welcome everybody to the second session. We have two talks. The first by Avrim Blum. Avrim is a professor at CMU. His research interests are in machine learning theory, approximation algorithms, algorithmic game theory, and AI planning. He's a recipient of the Sloan Fellowship. That's not the same Sloan as we had before. And the NSF Young Investigator Award, and also the ICML called 10-Year Best Paper Award. And we'll hear about distributed machine learning, communication, efficiency, and privacy. Avrim?
Thank you. First of all, I want to thank the organizers very much for the invitation. It's great to be here. So I'm going to be talking about some joint work with Nina Balkan, Shai Fine, and Yishai Mansour about distributed machine learning. So let me just start by saying a little bit about machine learning. So for the purposes of this talk, so what's machine learning about? We can think of it as making useful, accurate generalizations or predictions from data. So for instance, given access to maybe a sample of some population classified in some way, we might want to learn a rule that will have high accuracy over the population as a whole that we took the sample from. So just to, kind of have in your head some problems. A typical machine learning problem might be given a database of images, classified in some way, say images, male versus female, try to learn a rule that could correctly classify new images. Or given a database of protein sequences labeled by the function of the proteins, you might want to learn a rule that could predict the functions of new proteins when you just have the sequence information. Okay, so those are typical kinds of machine learning problems. Now, a problem that's become sort of increasingly important is that in many machine learning problems, we have actually a large amount of data, often distributed across multiple locations. Okay, and so, for example, it could be something like click data from some large search engine, customer data from a large company, scientific data where you have a lot of data stored in many geographically dispersed areas from different research groups generating the data. And so now, we have sort of a lot of data distributed in some way, but each entity only has, I want you to think of each entity having only a piece of the overall data pie. Okay, so there's some overall collection of data, but each has only a piece of it, a sort of a little bit view into it. And we'd like to learn something over the data as a whole. Okay, and in a setting like this, to try to learn over the combined overall distribution of data, the holders of the different pieces are going to have to somehow communicate with each other. So we want to think of them as communicating, sending messages or data or various pieces of information between them. And so a very classical machine learning question that sort of has been studied for over 40 years, are questions for a given type of learning problem, how much data do you need to learn a certain type of function well? That's a sort of very classic machine learning question. So I want to learn a certain type of rule. How much data do I need to see so that if I can do well in the data I've seen, I can have some confidence I'm going to do well on new data I haven't seen. And in this context, we can also ask the question, in addition to that, how much communication might we need in order to learn well? Okay, and so that's plus also issues like privacy. I'll talk a little bit about in this context, so that's going to be the focus of this talk. Okay, so that's the setting. So now there's kind of two high-level scenarios that are natural to think about in the context of distributed machine learning. One is you imagine that each location has data kind of from the same distribution. Okay, so you have data in many places, and each has maybe data arriving, and they're all from the same distribution, but each only has a piece of the overall. It only has a smaller number of data compared to the whole total. And so, in principle, each one could learn on its own once it saw enough data, but it would be slower, right? Because data is kind of falling in, and some goes to here, and some goes to there, and some goes to there, and each one could learn on its own, but only has, if there are sort of k entities, it only has a 1/k fraction of the data, so it would take longer. And so you'd really like to use some limited communication to speed up, ideally to the rate as if all the data was in one place. okay? And to do this with, I mean, of course, you could do that by everybody shipping their data to one place, but you'd like to do it with a lot less communication than that. There's actually been some very nice work on this setting of Dekel, Gilead Bachrosh, Shamir, Ohad Shamir, and Xiao. And the other extreme, and the extreme that I want to talk about today, is where the data is sort of arbitrarily, adversarially partitioned. Okay, so if you don't think of images of men and women, maybe it's not each as a random sample, but maybe the men are over there and the women are over here. So it's a orthodox database, I guess. Okay, so and so in that case, sort of learning to do this distinction without communication would be impossible, and that's going to be the focus of what I'm going to talk about. Okay. All right. There we go. Okay. All right. So I want to think about the following type of setting. We're going to try to learn some function of some type. So this is just a function in some class, just meaning a function of some type, like maybe a linear separator is a very common type of function we might want to learn in machine learning. Given labeled data coming from some overall probability distribution over some space. So we have points coming from some space, labeled as positive or negative. You might ask, well, maybe there is no perfect separator, but I'm going to make things simple, assume that when I talk about, say, learning a certain class, like learning linear separators, we're going to imagine there really is a consistent one. There is a good one that if you could find it, you would be able to do well. Okay? But this data is somehow arbitrarily, the distribution that data is coming from is arbitrarily partitioned among k entities. And I'll call them sometimes players, even though I'm not really thinking of a game. I'm not going to be looking at game theoretic aspects, but just we have k entities, and I'll just call them k players in this sort of learning game. Okay, 1 through k. And even just 2 is interesting. So a lot of things will be interesting even just with 2. We have this distribution is split arbitrarily into 2 pieces. Okay, so something like this, we have this overall distribution partitioned into k pieces, 1, 2, 3 up to k, where the overall distribution is the average of the d's. Now you could imagine a situation where maybe there's more data over there and less data over here, so that it's not an equal, you know, it's not 1 over k times each one. But let's just say that they each have about the same amount of data coming in, so that we care about the average of them all. Okay, so we have some overall distribution of data, but it's partitioned in some way that we don't really have control over among k parties, and we would like to somehow communicate to learn a function that's good overall. All right, so that's the setup. All right, players can sample from their own distribution, so they collect data, a whole bunch of data from their own distribution, and now they communicate, but they would like to learn a good rule over the overall combined distribution D, using as little communication between them as possible. All right, so that's the kind of setting I want to think about. And an interesting special case is kind of what I alluded to with the images of men and images of women, is you imagine just as 2 players, and they need to communicate. And maybe one has the positive examples and one has the negative examples. And so, you might ask, how much communication in this case would you need, for instance, to learn a good linear separator? Okay, so the point is, this guy can very quickly learn a rule that's good for predicting its new data. It knows it has positive examples of whatever it is. Okay, it's doing one kind of experiment, say it's generating positive examples of something. It doesn't need anything fancy to predict what the next thing is going to be. It's got positive examples. This guy here has, can very easily, it knows that the next thing it sees is going to be negative. What they really want is to find some rule that distinguishes this type of data from that type of data. Because this would be one special case that's of interesting to think about here. Okay, and they'd like to somehow communicate some information, and in the end, each of them end up with a good rule that could, given a new point, not knowing where it came from, distinguish, is it positive or negative. Okay. Good. And I want to think of, there's a couple regimes that one can think about. I want to think of the number of entities as small compared to the amount of data you would need for learning. Okay, you can imagine having many, many entities, each with maybe 0 or 1 point, and they need to communicate. But I don't want to think that way. I want to think of a small number, like 2, 3, entities. Each has a lot of data, but they don't want to talk too much. Okay. Good. Okay. So just to think about this, I think it's always helpful to think of, okay, what are your baselines? So what are sort of the easy things you could do? Well, first baseline is we know sort of a classic sample size results in machine learning say that any class of functions of a certain dimension, VC dimension, D, for instance, linear separators in D-dimensional space has VC dimension, well, technically D plus 1, but basically D. And you can learn that to error epsilon, some target error epsilon, think of 0.1, from basically order D over epsilon examples. Okay, so that if I have random examples of points in D-dimensional space, and I get D over epsilon points, find a consistent separator on that, I can be pretty confident it's going to have low error on new points coming from the same distribution. So it's sort of a classic sample complexity result. How much data do I need? If I can find a rule of some type that does well on that data, I'll do well on new data with high probability. Okay, so one very simple thing you could do is, hey, everyone just send data to one guy. Just elect one of the players, number 1, as the one that's going to do all the work. Everyone sends 1 over k fraction of this quantity here to player 1. Player 1 does all the work, finds a rule, and sends it to everybody else, and then you're done. Okay, so that's baseline number 1. We want to beat that. Okay? Good. Okay, so 1 round, and then this much communication. Okay, so that's one baseline. There's another baseline which is interesting to think about, which kind of goes differently. Suppose we are interested in a class of functions that has an online algorithm with some mistake bound. So this is actually more like the type of thing that Manuel was talking about. So what do I mean by an online algorithm with a mistake bound? It's an algorithm that sees inputs one at a time and makes predictions. Is this thing positive or negative? Is this positive or negative? And it guarantees that as long as the labels are being given according to some function, say a linear separator, some bound on how many times it makes a mistake. Okay? So a very classic example of this from the 1960s is the Perceptron algorithm. It's an algorithm for learning a linear separator, and it has the following property. If there really is a separator in the world that separates the positives and negatives, and not only separates them, but by some margin of separation gamma, okay, in order to make this dimension, sort of the units right, think of these points as scaled to lie inside the unit radius ball. Okay, and then there's a well-defined how much separation do you get, say that's gamma. And there's this nice algorithm called the Perceptron algorithm. It's very simple. It has a very nice guarantee that it can make predictions, and sometimes it'll make mistakes. When it makes mistakes, it updates itself. And it's guaranteed to make at most 1 over gamma squared mistakes. That would be an example of something. It's an algorithm that, for a function of this type, makes at most this many mistakes. Okay, so suppose you have that. Then here's a very natural thing, which is player 1 will be the one who runs the algorithm, and it's going to broadcast the current hypothesis. Actually, everybody can be running it in parallel, but let's just think of player 1 as broadcasting the current thing. And anybody who, if it doesn't work on their data, any player as a counterexample can raise their hand, throw the counterexample in the air. Okay, so the communication model I'm imagining is, say, broadcast. You can, and let's not worry about synchronicity and collision. Just anyone has an example can throw it out and say, hey, here's an example I have. The thing didn't work on. Player 1 or everybody who's running in parallel sees the example, updates, and you all have a new one. And then anyone have, does anybody have in their data set anything that makes a mistake? If so, the first, somebody gets it, tosses it out, and then everyone does an update. Okay, so that's another baseline. And there, the number of examples that will be transmitted is at most this quantity m. Right. So that many examples communicate. Right. Okay. Everyone all right? Yeah.
Actually, sort of a conceptual problem with this baseline, the example you gave with all the positives being at D1 and all the negatives being D2. Each of them would think his
the goal of, say, player 1 is not to get a good rule on D1. So I'm kind of imagining that data is cheap for each player. If they wanted to get a good rule for their own data, they could do that without talking to anybody. So the point is, as all the positives, they say, there is no such thing as negative examples, everything in the world's positive. And this person says, there is no such thing as positive examples, everything's negative. What they want to do, they know that they only have a piece of the picture. They know that they're doing a certain kind of experiment, these guys are doing some other experiment, or whatever it is. They have certain types of data. They know that they want to do well on the combined thing. So their goal is at the end of the process that each of them should have a rule that does well given a new point from the combined distribution, not knowing where it came from, right? So if say the images of, I don't know, men are here and women are there, then what you want is each of them at the end should have a rule that given a new image, not being told where it came from. Once you knew where it came from, you would know what to do.
It seems like part of this baseline would be to make at least the assumption about their existing more data, which might be have this or that value that's not known to you, rather than start with an hypothesis just on your own.
Okay, good. So maybe I didn't say the baseline clearly. So there's a particular algorithm. They're going to be running it in lockstep, not on their own data. They're all going to have the same piece of code running in lockstep, or you could think of just one player running it, and only running it on the data that's been thrown in the air, not on your own. So for instance, the Perceptron algorithm starts with the 0 vector. So it says everything is negative. Anyone with a positive example throws it in the air. They all lock, so they're all running in lockstep, right? Because once they start getting out of sync, you could get into trouble. Good. Okay, good. Absolutely. Good. So we have here two baselines, one with a linear dependence on this VC dimension and linear in this error term. The second one depend on this mistake bound n, which is typically larger than this quantity here, but had no dependence on the error rate. The number of examples transmitted had no dependence on the error rate, the final error rate. And so it's natural to ask if you can sort of do better. One thing you might want is maybe linear in D and say at least a smaller dependence, say logarithmic in the error term. Could you, for instance, do that? And it turns out the answer is yes, you can do that. And this is sort of nice. It ends up being a distributed form of the boosting, ADA boosting algorithm, which is so the ADA boost algorithm is a very kind of powerful algorithm in machine learning, and it fits very nicely in this distributed learning context. Let me describe how it works, and you'll see it's very natural. Okay, I mean, it's a very natural thing to do. So here's the idea. Let's just run the first baseline for some fixed error rate, like a quarter. So that's not going to take too much data. So everyone's going to send a little bit of data to the first guy. It finds some rule that, say, has error a quarter overall. So a quarter, think of as being, it's better than a half. Not as good as, as 1%, okay? So everyone sends a small amount of data to the first player, enough to learn to some modest error rate. Now, first player gets some initial rule, sends it to everybody else. So now what players can do is they can look at that rule. And then they can imagine taking their data distribution. So maybe this is so maybe data wasn't distributed pluses one place minuses. This guy's got pluses and minuses, but that first rule looks like this. So this is the more plus side, and that's the more minus side, right? But it made some mistakes here, and it made some mistakes there. So a natural thing to do is to reweight their distribution, to focus more attention on the parts where this rule did poorly. Okay, and then send, again, now to player one data, but not from the original distribution, but rather the reweighted distribution where the previous rule did poorly. So if you think about it, it's a very natural thought. If you're just sending, random samples of your stuff to player one, maybe, you've already have enough data to really understand what to do in certain parts of the space. There's some other weird parts of the space where you don't really understand. So you'd like, in each round, to focus attention on the parts of the space where you're doing badly, give data of that type. Now player one gets this new kind of data and can then improve and find a better rule. And so what this ends up being is a distributed implementation of the ADA boost algorithm. There's various low-order communication that you need too. For example, the current rule sent may not do equally well on each person's data. It may do really well on this person's data, really badly on this person's data in the middle here. And in order to run the AdaBoost algorithm, you want to focus not just per player on, the parts where it's doing well, but also the players where it's doing well already should kind of shut up and let the players where it's doing badly send more stuff to player one. Okay, and so they have to send a little bit of back and forth to say, hey, how is it doing? So the player one knows to request more data from the ones where it's doing badly and less from the ones where it's doing well. And if you do this and do it right, you end up being able to simulate this AdaBoost algorithm. I'm not going through the proof of, there's a theorem one needs to prove, which is that AdaBoost works correctly, but I don't want to do that. We're just going to basically simulate that. And the key point is that each round only uses order D samples independent of the target error rate, and is able to basically cut the error rate down multiplicatively. So basically every time you do it, it cuts the error rate down multiplicatively and only uses order D communication, which is great, because to get down to 1%, you only need log, that many steps to cut down multiplicatively. And so that way you can get this sort of good communication per round, some extra bits that I didn't really talk about, plus not too many rounds of communication. Yeah.
All of the examples is like the total over the k players or for which players?
Total, right? So, yeah. So each is sending the d over k fraction. Yeah. D, 1 over k fraction. Yeah. Okay, good. So this is nice because it gives only logarithmic depends on the error rate in terms of communication. So it's a way of doing this where the players end up not having to communicate the data, which player one kind of already is doing well on. Okay, so that's kind of a generic statement. I didn't really talk there about what type of functions we were interested in. And it's interesting in this context to look at what can you do for specific classes of functions. And I thought I would mention here 2 classes of functions where I think there's something kind of interesting to say and where there's some nice open questions too. So let me start with one, which is not the most natural class from a learning point of view, but very nice theoretically, which is parity functions. Okay? So parity functions, are some very nice kinds of functions. From a machine learning point of view, it's rare that you actually have, something where, gosh, is this an image of a dog or a cat? Well, it depends on whether an even or odd number of certain features are true. It doesn't come up that often, but okay, nonetheless. All right, parity function. So what do I mean? Our examples are d-bit vectors. The target is given by the dot product of the example with some unknown vector. I'll call VF is the vector for the function, mod 2. All right, so this is what you're trying to figure out for some unknown vector V. Okay? You're going to be given some data, and you want to be able to learn this function. Okay, good. So this is interesting even for just 2 people. So we'll do it for 2 people, also because you'll see in a second. So it turns out there's a classic communication lower bound for determining if 2 subspaces intersect. I've got some vectors, you've got some vectors. We want to tell if our subspaces intersect. And what this means is, in terms of how many bits of communication, it gives us a d² lower bound in terms of bits of communication if our goal is to actually find a good V. Nonetheless, maybe we can do with less communication if we just need to be able to predict F well, even if the rule we have in our head is not defined by a vector V. So the way we're going to get around this is by allowing ourselves rules that don't look like x dot something. Okay? All right. So what I want to do is beat d² bits of communication. Okay. Notice that the previous kind of bound would have matched this in the sense that each example is d bits long, and sending d examples, that's d² bits, but I want to beat that. Okay, so here's what we're going to use. This is only going to work for 2 players, okay? So the open question is, can you do this sort of thing with 3? Okay, but here's what you can do with 2. So parity has interesting properties. There's 2 kind of different algorithms that you can use. They each have different properties. The first algorithm is you can learn it. It's called properly learned, meaning learn using a vector in a very natural way. Okay, so you can do that. All you got to do is you sample a bunch of points, t over epsilon points. You get a bunch of linear equalities, mod 2, right? So whatever this unknown vector is, dotted with the first example gave you something like a 1, dotted with the second example gave you something like a 0, dotted with the third example gave you something, maybe it was a 0, dotted with the fourth, blah, blah, blah. You take that, you get a linear system, you solve it with Gaussian elimination, and boom, you get a vector. Okay? That's one way you can learn. Another way you can learn is the following. So this is there's this model called the Reliable Useful Learning model of Rivest and Sloan. And the Reliable Useful Learning model is a model that says the following. You're not allowed to make mistakes. Okay? I want a learning algorithm that's going to take data and output a rule that's not allowed to make mistakes. But it is allowed to say, I don't know. Okay? You can either make the right answer or say, I don't know. Those are your choices. And you shouldn't say, I don't know all the time. Okay? Because that's easy. You should say the right answer, like say, 1 minus epsilon fraction of time, epsilon fraction of time, you're allowed to say I don't know. That you can do also. The way you can learn, so think of it, right? This is not going to be hard. We can learn parity functions in that model too. What you do is you draw a reasonable size sample of data, and now you don't do any processing on it at all. You wait until the point comes in. When the point to predict comes in, you see, can I write this new point x as, is it in the subspace spanned by my training data? So my training data are the ones I got with the labels, the positives and negatives. I got a new point in, I need to make a prediction. Can I write it as, a sum of training examples? So is it in the subspace spanned by them? If so, if, this example is, the first example, the new thing came in as like the first example plus the fourth example plus the fifth example, mod 2. Well, its label better be this guy's label plus that guy's label plus that guy's label, mod 2. Right? So if it's in the subspace, I know what to say. If it's not in the subspace, I don't know. I just say I don't know. Okay? The key distinction between these two for our purposes, this one doesn't make mistakes, right? So that way it's better. But this one is more compact. This one outputs a vector. This guy just stores a bunch of data. So what you can do with 2 players is the following. Each player learns both ways. Right? They take their data, learn both ways. They get a parity function, so the G is going to be a parity function. They also run the other way, which is stores a big stack of data. They can't send the stack of data over to the other guy, but they can send the parity functions over. Now, each will have a rule that does well. They'll each have different rules. But they'll each have a rule that does well on the overall distribution, where the overall rule is first run the stack of data rule, the one that doesn't make mistakes. It just gives the right answer, says I don't know. If that rule makes a prediction, you know it's right, so go with it. If it says I don't know, then use the one I got from the other guy. Does that make sense? So, see, what's happening is, they may have data that really span different parts of the space. And so, if you just use the parity function, let's say you use the rule you got from the other guy, it might be that the G works really well in your data and really badly on the other guy's data, and vice versa. And so given some new point, how are you going to know if the G is good on it or not? The H at least tells you, gives you the right answer or says I don't know. So you can use that one first, and then if that one, as long as I use the other guy. So one way to think of it is, if the new point was coming from my distribution, my H should work well, because I trained it on data from my distribution. If the example is coming from the other guy's distribution, maybe my H says I don't know. But that's okay, because the G worked well in his distribution. So if the H says I don't know, I'll use the G he sent me. Okay, so nice question is, what can you do with 3 people? Okay, with 3 people, unclear. You can have 2 sending you their G's, but then what do you do? Like, one of them works well in one works well in the other. Okay.
That's the open problem.
For here, yeah. So that's, what can you do with 3? Yeah. If you like, you can think of the third one as like, sure. Just 3 people. I was going to say, you can think of the third one as like not really having any data at all. Like, neither one can communicate this rule to a third party, for example. That's one issue. Okay. Here's another one, also as an open problem. Linear separators. So, learning linear separators, it's convenient to just think of them as going through the origin. In that case, you can think of the points as all lying on the sphere. let's say we have a near uniform probability distribution on the sphere. That's kind of an interesting case because in that case, all the sort of common bounds people use all give you the same answer. If you see dimension bounds, something called margin bounds, the perceptron mistake bound, they all say you're going to need order D examples to learn. So you're going to kind of need order D examples of communication using these baselines. Okay, so I guess just be clear that right now I'm being slightly fuzzy communication-wise because I'm talking about points in real space. What does it mean to communicate them? And you can pack anything you want in a real number. And okay, let's just assume that the algorithms have to be sort of reasonable. Otherwise, we're going to have to talk about either precision or noise or something. But, okay, we're all among friends. Let's just say we send examples just to be reasonable about things. Okay. All right. Okay, so it's not, can we beat the order D? Here's an idea that's interesting. So this algorithm called the Perceptron Algorithm, I didn't define it, but it's a very simple algorithm. And what it does, I'll just tell you what it does. It has a vector, and it sees, remember, so what is it we're trying to do, right? We want the, all right, here's the vector. So we want dot product positive on the positive examples, negative on the negative examples. If you make a mistake, all the algorithm does is, if there was a positive over here, I add it to my vector. If there was a negative over here, I subtract it from my vector. That's all the algorithm does. When it makes a mistake, it adds or subtracts the point from its vector. It's very, very simple. And you can run it until it gets the points. So what you have is, let's just imagine we run round robin. Player one starts running the algorithm on their own data until they get a vector that works well on their own data, separating it by some reasonable margin, say satisfying something like this. So this separates your own data by reasonable margin, sends it off to player two. Player two, okay, good. Oh, whoops, let me go like this. Okay, so we're going to send it to player two. Player two is going to take the vector we got from player one, start from that point. So now it's going to be different. They're not going to be running lockstep. Player one's done, sends it to player two. Player two takes the current rule, looks at his own data. If it does correct, great, sends it on. If not, update until it satisfies this condition on its data, sends it on to player three. Player three, then it goes back to player one. We're going to go around like this until the players are happy. Okay. And here's a nice thing. As long as the points of player I and the points of player J are reasonably orthogonal to each other, that means the updates of player J don't mess too much with the data of player I, because what you're doing in this algorithm is adding and subtracting, the examples. If they're reasonably orthogonal, it's not going to change the dot product by too much. So this is nice because it means that when you send along to the next guy, if they don't make too many updates, so you see, before you send it along, you made sure that it got your data right and right by a good margin. So that means a few updates, it's not going to affect the dot products too much. You have some space, some wiggle room there. So a few updates, no damage. A lot of updates might cause damage, but a lot of updates means the algorithm made a lot of progress. See, what you don't want is like one update, send, one update, send, one update, one update, one update, one update. It's too much communication for the amount of progress. You want a lot of updates, send, a lot of updates, and so forth. And you get a lot of progress. And so when you work out what happens is that if the overall distribution is near uniform, you end up, rather than D examples, and D vectors communicated only about square root of D. So, and an open question is, can you get similar savings for more general kinds of distributions? Okay. So the last thing I wanted to just talk about briefly is kind of privacy. It's so natural to think of privacy in this context. And what I want to talk about is privacy in a different sense of, not in the sense of secure function computation, but more in the sense of differential privacy. So here, I'm sort of imagining that everybody's got some data. Data elements, could be patient records or customer records or click data. And we'd like to preserve the privacy of the individuals involved. And in this context, there's a very nice, compelling notion of differential privacy that's been studied, which says if you take any one record and replace it with a fake record, so there, just replace that with a fake record, then nobody else can really tell what can tell. So if information theoretically, and through the communication, nobody else can tell. Okay, and so formally, what you want is that for any sequence, sigma of sequence of interactions, the probability that given the actual database you produce the sigma compared to the probability on the pretend database that you produce a sigma, where you just change the one entry, they should be pretty close to 1. So that basically it's a model of plausible deniability. If I wanted to pretend that was my row rather than the actual row, you can't really tell. Okay. And there have been a number of algorithms developed for doing differentially private learning in the centralized setting, and you can ask how you can maintain differential privacy without increasing communication by much. Okay? But actually what I want to talk about just to end is there's a different kind of privacy that I think is interesting to think about, which is sort of privacy for the data holder. Okay? So, think of the data holder as some sort of hospital, say. And I think what's natural to think about from a machine learning perspective is to think of the distribution as being not sensitive information. So the distribution, DI, is like statistical information about the population of people who are sick in the hospital, who are sick in city I, whereas SI is the actual set of people in your hospital. So the sample is sensitive, the distribution is not sensitive. Those are the actual patients. And the question, and the natural thing you might want to do is, can I reveal no more information about the sample than is inherent in the distribution that it came from? That's sort of a natural kind of privacy. And it's different from differential privacy. It's not stronger or weaker, it's just different. It's not, for instance, not guaranteed by differential privacy. Consider the query, what fraction of the sample, say, has HIV? Okay? Differential privacy allows taking the sample, computing the average, finding the fraction, and adding noise proportional to 1 over the sample size. Okay? But that can be smaller than the sample variation, 1 over square root of the sample size. So you get 2 hospitals in the city, and one of the hospitals answers this. From the answer, you could tell, after later, maybe I don't know, things are opened up, you could tell which hospital it came from. Okay, so so it's not preserving this kind of privacy. So it's natural you can define this. So basically you have the protocol interacting with your data. And you'd like to reveal no more information about your data other than is inherent in the distribution. And you can sort of model this as saying, if we were to instead draw a fake sample, interact with this instead, this poor guy shouldn't be able to tell the difference. Basically just says the poor guy shouldn't be able to tell the difference. And so it's interesting, you can think of that here, and then you can talk about getting algorithms with this kind of guarantee. And so you can do that in many cases without increasing the communication overhead too much. Okay. So let me end. So as we move to large distributed data sets, communication issues are becoming important. There's been sort of increasing interest in what do we, in addition to asking how much data do we need to learn well, in addition to asking about running time, it's also very natural to ask how much communication overhead do we need, especially in cases where communication is expensive, maybe energy expensive, or just they're far apart. And then also issues like privacy become more critical. And there's actually quite a number of open questions here. I mentioned a couple, but there's a lot more. Okay. That's it.
Question?
Hey.
So in the results you mentioned, the first 2 results, they're all in the noise-free setting?
Yeah, this is in the noise-free setting, right? You could also look at either the agnostic setting, where it's sort of arbitrary, or maybe a random classification noise type setting. But this is all noise-free.
So whether you don't know of any results?
With some results, not as many. So a few kind of one problem in the case of worst case noise is even if polynomial time centralized algorithms are often hard without extra assumptions. But we have a few sample, just like not worrying about running time results, but not as much. Certainly most of what we know is in the noise-free setting. There's a little bit, but yeah, it's a lot.
About the parity results, do you consider the possibility of communicating not just the hypothesis, but a small function which also produces the hypothesized value and the degree of certainty? And then when these are exchanged, instead of using your own stack of data to determine whether or not, you can use others' estimate of how well or how good their prediction regarding the...
Yeah, it's all fair game. I mean, I think from the point of view of the open question, you want little o of d squared bits, okay, to communicate something, and you can use those bits to mean whatever you like. And what I was describing is just something that we know works in the case of 2, and we don't know anything that works for more than 2. I mean, anything that works is fair game. So, you know, if it can be made to work, great.
Any more questions? Well, I have one question. What happens if one of these agents applies a specific, let's say, classifies according to a linear separator, and the other one, and the other agent does it in nonlinear fashion? So the bad or the bad examples that they transfer from one another may be irrelevant to the other one. Let's say that the linear separator finds, this misclassifies certain part, and so the amount of the relevant information that it transfers to the non-linear classifier is low, because these are not the examples that are really bad or bad for the non-linear separator.
I guess one thing is that the setting I'm thinking about, there's sort of a collaborative, you know, everyone's trying to find something that does well on the overall data as a whole. So I'm sort of imagining that like none of the players is being sort of adversarial and, you know, doing something different. It's like in this case, they were all, you know, they're all trying to find, say, a linear set. But you could certainly, I'm not sure I understand. Okay, maybe we should take it offline.
Okay.